In the last lecture, we have seen the essence of computational fluid dynamics approach to the solution of a partial differential equation. We discretize the flow domain into small cells. We distribute a number of grid points within the flow domain, and then we write finite difference approximations for each of the derivatives that occur in that equation, and then convert at that particular point the partial differential equation into an approximate difference equation featuring the variable values at the grid points as the unknowns in that equation. And usually this equation requires knowledge of the neighboring values at the neighboring grid points also, and so we have to do this for every grid point where we want to have a solution, and then in the process we also make use of the boundary conditions, and we convert the partial differential equation into a set of algebraic equations, and then we go through some specialized techniques for the solution of these algebraic equations. Now this particular approach is very good, it is flexible, and before we go much more deeply into the underlying concepts which will actually give us an idea of how to go about it systematically for complicated cases, we would like to introduce a different kind of problem which again looks very simple from the outset, but when we actually want to deal with it, it becomes a bit more complicated. And this is the case where we would like to look at flow through a triangular duct, a fully developed flow through a triangular duct, which is different from what we had earlier. This is a duct of triangular cross section, and again we have x going like this, y vertical, and z going in the outward normal direction as per the right hand coordinate system here. And so you have flow going through this, and we would like to see how the velocity changes here. Again here we have the case of steady fully developed laminar flow, and we will see that again we have the case of u equal to 0, v equal to 0 everywhere, and w is not equal to 0, and it is governed by the same equation that we had in the previous class, which is dou square w by dou y square plus dou square w by dou x square plus dou square w by dou y square equal to c, where c is the pressure gradient, is a constant involving the pressure gradient in the z direction. Okay, so we have this, and we need to solve this for this particular shape with the same boundary condition as before, that is with w equal to 0 on all walls as the boundary conditions, okay, as the boundary condition, and this is the problem that we would like to solve. Okay, so if we want to go about this problem in the same way as we had done earlier, we'd have to put points at intersection of coordinate lines. Remember that for the rectangular duct we drew constant lines of constant y like this and constant x like this, and then we put the grid points, and then we express the derivatives in terms of the neighboring points here. And here if we want to do the same thing, we will have difficulty because this line here is inclined and this line is inclined, and it's not possible to have a similar kind of grid in this triangular cross section. And this problem persists not just for triangular cross section, even for a cross section like this, even for a shape like this. And in such cases, simplistically speaking, it's very difficult to use this way of doing the CFD solution. These kind of shapes are not uncommon. In fact, as we saw in the example of the T junction, where we are looking at shaping the junction in a certain way, like this, we have a shape here which cannot be put in a mesh like this, in a Cartesian mesh like this. Okay, so but we still need to compute the flow going through this and then coming out partly and coming out partly here. So when we have these kind of irregular geometries, then the way that we have used here, that is using lines along lines of constant values of x and y to identify the grid points, is not going to work easily. So it is very cumbersome, and it's going to give us lots of problems, and it brings in approximations. So for problems like this, which are really quite common, we have a different approach, and that approach is what we are going to study in its simplest form. We go through the same argument as what we had done earlier, which is replace the partial differential equation with an approximate form at a grid point, and then we do that for every grid point, and that results in a set of algebraic equations in place of one partial differential equation, and then we go about solving it. But the way we convert the partial differential equation into algebraic set of algebraic equations is different in this particular case, because we cannot fit a triangle into a rectangle here. It's possible through a coordinate transformation, but it's not so easy to do that, and it requires advanced level of mathematics. So we'd like to use another intuitive approach for the solution of this particular thing, and the power of this method is what we will show shortly. So the basic idea is not to be restricted to have these kind of rectangular cells making up this, but we can have cells like this. We can have triangular cells, okay, and these triangular cells, we would like to then solve this equation around this, and this kind of triangular cells kind of thing can easily enable us to deal with even a geometry like this. Okay, so if you have a curved domain like this, we segmentize this by putting number of points. We make it into linear segments. And then we can join them by straight lines. So this is what we mean by linear segmentations. Where the curvature is too much, we can put smaller segments. For example, here we can put 2 small segments and make it like this, and then we put lots of points in between. And then what we call as join them by triangles, so that the whole shape inside the flow domain is now made up of tiles of triangular shape in this particular case. Okay. So if we have a way of dealing with a non-rectangular mesh, this is known as unstructured mesh. So, if we can describe our flow domain in terms of an unstructured mesh, and if we have a way of converting our partial differential equation into an algebraic equation at the center of this, then we can get a value of this here at the center of this, at the center of this, center of this, like this. And if you make them small, then you can get many more points. So, this approach, the approach which is used to convert the partial differential equation into a difference equation, okay, into an algebraic equation, we have done this using finite difference approximations. Where we have substituted a formula for dou square W by dou x square, which is valid only when the grid points are along lines of constant values of the coordinate lines. And here we do not have the grid points here along lines of constant values of coordinate lines. These grid points are not arrived at the intersection, are not located at intersections of constant values of coordinate lines. And for this case, you cannot write down the previous finite difference approximations. So, what we do is that we use a different approach which is known as finite volume approach. So, using finite volume approach, we take the governing equation like this, and then we integrate the governing equation over a cell. For example, in this particular case we have a cell here, we integrate this, and using that, in the process of integration we will convert this into an integration across the faces, and then we can evaluate the fluxes associated with this, and we make use of estimate the fluxes and then convert this continuous partial differential equation into an approximate form valid at the centers of each of these cells. So, that approach is known as the finite volume approach, and as a result of this discretization, we end up again, just as we have done in the other case, equations which describe, which have variable as variables the values of W at all these nodes. So, the only difference between the finite difference method and the finite volume method is how we do the discretization of this equation at these discrete points located throughout the domain. So, at the end of this discretization, we again have a set of equations which can be written as AW equal to B, and in many cases we can make use of the same solution techniques for the solution of this as we do for the finite difference methods. Not in all cases, but definitely in many cases. So, in this lecture we are going to look at the finite volume approach. We would like to get an introduction to the finite volume approach of converting a partial differential equation into a set of algebraic equations. We will look at specifically for the case of a triangular cross section. Before that, I would like to show some pictures which will show you what kind of how a finite, a triangular mesh looks different from this. How we Okay, yes. Imagine that we are looking at this funny face that you see on your screen here, and this has, it's a circle with 3 triangles, maybe the mouth and the 2 eyes, and we would like to describe this. We would like to convert, we would like to put lots of grid points here in such a way that we can solve the Gaussian equation at these things. And here we used a special algorithm which we will discuss later on to put the grid points, locate the grid points throughout the domain here and only within the domain, because what is there here, this part is not in the flow domain, this is outside the flow domain. Again, this outside the flow domain, you can see that there are boundary points which describe this, and there are no grid nodes in the domain outside here and here and here. So we distribute all these grid points and then we make use of special algorithms to join up these grid points, interior grid nodes and then the boundary nodes in the form of triangles here. And we need specialized algorithms here because we do not want overlapping of the triangles. We would like to make sure that when you join up all the triangles, we cover the entire area, nothing more and nothing less. Okay, so and this requires an algorithmic approach, because in a case like this maybe we can join by hand, but in a more practical case, difficult case, we would like the computer to do it, because it will take a very long time for us to do it manually, and so we need to have an algorithm for doing this, and we look at certain algorithms later on in the course. But the point is that we can describe a face like this with part of the circle here and a flat face here and something like a triangle openings here and all these things, and we can make the grid points closer together to make a fine grid. Okay, so this is the power of triangulation, and we can represent any arbitrary geometry using this kind of approach. Now we would like to see how, having done this triangulation, how we can then use the convert the partial differential equation into approximations, how to derive the approximate form of the partial differential equation at the center of each of these nodes. So that is the objective of the lesson that we are going to do today. So let us go back to our triangle. This is our triangle, and the yellow face is what we are going to look at. It is a 2-dimensional domain, and we would like to know the velocity at any point within this. That is in theory, but in CFD we do not give at any point, we give only at select points. Okay. In the case of finite difference approach that we have seen in the first example, there we located the grid points at intersection of the coordinate lines, and we do not have that luxury here, and so we will locate them, we will do a different kind of discretization. So for this simple case, especially in order to understand the principles and in order to do it by hand, we have divided this equilateral triangle, which we have taken for simplicity, into 1, 2, 3, 7, okay, 9 equilateral triangles here. Okay, so we just said, okay, we will divide this into 3 parts, and we will divide this into 3 parts, divide this into 3 parts, and we can easily make a triangulation here without too much of difficulty. And what we would like to do is that we would like to say that in this case we would like to know the velocity, the W velocity at the centroid of each of these triangles. For example, if this is one triangle here, the centroid is given by the point of intersection of these lines here. So, this is going this point is the midway point for this side, and this point is the midway point for this side, and we locate the grid node at which we want to evaluate the velocity at the centroid of each triangle. So, similarly, if you consider this adjacent triangle here, for example, if this triangle is this triangle, you also have an adjacent triangle. So, for this also we locate at the centroid, and for this also we locate at the centroid. So, at the centroid of each of these triangles, we would like to have the velocity. So, that means that the first step of finding the solution, which is determining the nodes at which we would like to deliver the velocity, is done in the following way. That is, we triangulate the domain, we split it into triangular cells. In this particular case, we have the luxury of making it into equilateral triangles, which is not necessarily the case in general, but we can convert it into triangles, and then we say that at the centroid of each triangle is the point, is the node at which we would like to have the velocity. So, in this particular case, we have 9 triangles, and we would like to have velocity at this centroid here, this centroid here, this centroid here, here, and so on. So, how to go about it is the next thing. So, if you take a triangle here for an equilateral triangle, the centroid is located from the vertex at 2/3 of the distance, where h is the height and L here is the length of the thing. So, this is located at a height of h by 3 from the bottom and to h by 3, and it is also important for us when we do the conversion of the partial differential equation into an algebraic equation by writing an approximate form of the partial differential equation at the centroid. We need to know what is the nearest distance to the walls. So, here we would like to know what is the center of this wall here, and center of this side, and center of this side. So, for this particular case, the center of this side is located at midway point here, and this again midway point, and this midway point is such that it is a distance of h by 6, where h is the height, and L by 4 from the centroid. So, these are the kind of geometric information which we can deduce for any triangle. So, this information will be needed for us in order to convert the partial differential equation. Now, how do we do this conversion? So, we will go back to the board so that we have control over it. So, we have our governing equation like this. When we are doing the finite volume approach for discretizing this, okay, writing an approximate form of this over an unstructured mesh having not necessarily a rectangular cross section like this, triangular or polygonal cross section, okay, of an arbitrary shape, we would like to convert this equation, write this equation in a special form known as the conservation form. Okay. And right now we do not want to know too much about it, but we see that this is a Laplace equation, Poisson equation, and the left hand side here is equivalent to, in vector form, del square W equal to constant. Okay. And we can also write del square as del dot gradient of W equal to constant. So, when we go through the equations and all that in the next module, we will be able to see how this whole thing comes about here. But for the moment, we say that this equation can also be written like this, in vector form, and it can also be written like this. Okay. So, now we take any of the cells here and we integrate this equation over the cell. So, we write del dot del omega or del W integrated over the entire closed surface of cell I, okay, is also equal to the integration of the constant over the closed surface of the same I of the same cell here. So, we have a cell I here and cell J, cell K like this, and we can do this. So, this is a governing equation. We can do any mathematical operation with that, and we choose to have an integration over the closed boundary of that particular cell as the mathematical operation that we want to do with this. So far, we have not done anything other than rewrite the equation and do a mathematical operation on it, which does not compromise the solution in any way. Now, this is a special type of integral here. This is a divergence of the gradient of W here, which is being integrated over a closed surface, and we can make use of Gauss's divergence theorem to convert this equation, which is integral over the area, into integral along the boundary, closed boundary of that particular cell. Okay, so, the left hand side is written like this, where n is the normal vector and this is the gradient, and the right hand side is just C times the area of the cell. Okay, so, the right hand side is just the constant value times the area of the cell. So, let us just see what we are at. Let us say we have a triangular cell like this. This is the centroid of the cell I here, and we are integrating this whole quantity over this entire area. Okay. And this is what this equation tells us. And what this equation tells us is that you just evaluate the gradient of W at each of these faces, because the this area is covered by these surfaces here, and then you take the outward normal vector of each face, and then you take the dot product and then sum over all these things. Okay. So, that is what we are, instead of evaluating this whole thing over the, one evaluation of this will be to do this over each area within this and then sum it up. The other possibility which allows us, which Gauss's divergence theorem allows us to do, is to evaluate the gradient along the face, along the three faces in this particular case, and then take a dot product of the normal vector with this. So, that means that so instead of it becoming an area integral integrated over the entire area, we just have to evaluate the gradient only along the surfaces. So, assuming that the cell is small and the gradient does not change like this along the length here, we can therefore write this as, discretize this as sum over all the faces of the triangle n dot okay. So, this is a continuous integral along the length. You start from here and then you go along this, and then at each point you evaluate the surface normal vector and the gradient, and then you integrate over this. Okay. So, you take a small dl here and then you evaluate the local gradient, and then you take the local surface normal vector, take the dot product, multiply by this, and then you move on to this. So, if the cell size itself is small, then we can approximate this as at the midpoint of this side I evaluate the gradient, and then I evaluate the surface normal vector, and then I take the dot product here, and then I multiply by the length of this side. So, we can write this by putting A here and B here and C here like this. We can write this as n dot gradient of W over side AB times length of side AB plus n dot gradient of W side BC times length BC plus n dot gradient of W over side CA times length CA is equal to the constant C times area of the cell ABC. Okay. So, this summarizes for us the way of converting a partial differential equation into an algebraic equation. Not quite algebraic equation at this stage, but we are going through a discretization from a continuous partial differential equation into discrete values of the gradients evaluated over the midpoint of each of these things. So, we evaluate the gradient at the midpoint of this, and then we multiply by the surface normal vector here, and then the length here in order to get this. So, we do that over this space and this space and this space. If the shape is like this, if this is a cell, we can do the same thing over each of this P, Q, R, S, T, U, V, W, X. So, it will be a sum over, so you evaluate the outward normal vector and then the gradient, and then the gradient outward normal vector like this, and then on this. Now, what is this gradient here? It depends on, you have a cell node and you have a W associated with this, and you have another cell here, and this is part of another cell here, and if you know this value and this value, from this you can evaluate the gradient. So, you evaluate the gradient in terms of the differences change between the node value and the neighboring node value, across which you have this face as a separation. So, in that sense, this is, although this is a gradient and at this stage it is a partial derivative, we are going to evaluate this in terms of the difference between the value of W at between the neighboring cells, between the node, this node and then the neighboring node. So, in that sense we can convert, we can evaluate this at discrete points and then convert in the process the partial differential equation into an algebraic equation valid at the center of, at the centroid of this particular triangle. So, this is the way that we can do the discretization. In the next lesson we will actually work it out fully.